Hello, my name is Dave Farnia, and in today's webinar we'll be talking about 3D motor analysis with JMAG. We'll start off today's webinar with a short overview, and then we'll see what does 3D modeling do for you. We'll perform some 3D analyses, and then look at how we can increase 3D simulation speed. Finally, we'll conclude with a short summary. So, as for an overview, why is 3D analysis necessary? Well, 3D analysis can model actual phenomena more accurately than 2D modeling. 2D analyses may be adequate when modeling geometry and the main magnetic flux in a motor, but some phenomena, such as leakage and skew, are inherently 3D effects and thus require 3D analyses. Setting up a 3D model can be more complicated than setting up a 2D model, but there are many techniques that can reduce this complexity. So, what does 3D modeling do for you? In our first example, we'll look at torque with magnetic saturation. As a motor's aspect ratio, which is defined as the axial height divided by diameter, decreases, leakage effects increase. This is most apparent in magnetically saturated regions. For the analysis example, we'll look at an IPM motor with varying aspect ratios, and we'll benchmark the torque against the nominal value of 30 millimeters in complete axial height. The effects of the axial length on the magnetic flux density distribution are shown when 32 amps of current is applied to the coil windings. We can see that saturation increases as the axial length is shorter. In our benchmark model of 30 millimeters, we can see that the average tooth flux density is about 1.8 Tesla. But in our model that's got 1/8 the axial height, we can see that the average tooth flux density goes to 2.2 Tesla. So the tooth flux density increases significantly due to the effects of leakage. The effect of the axial length on the average torque is shown with a current value of 1 amp and a current value of 32 amps. The average torque is converted to values based on the 30 millimeter axial height. As we can see, the effects from leakage flux are more dramatic with higher current and saturation. If we take the values of average torque at 1 amp of current, we can see that the 1/8 axial height motor has an average torque that's only about 4% lower than the benchmark model of 30 millimeters. But if we increase that applied current to 32 amps, we can see that the average torque drops by more than 40%. So, if we look at the results from this analysis, we can see that for smaller aspect ratio models or decreasing aspect ratio models, it's absolutely necessary to actually do a 3D analysis instead of relying on a 2D model or extrapolating based on a higher aspect ratio model's results. We can also see that in the effects on coil end inductance. The increase in inductance from leakage flux linking coil ends is typically estimated at 10%. But inductance can be accurately evaluated by modeling the coil ends in a 3D analysis. Then, a 2D model's inductance can be corrected based on the results from that 3D model. So, let's look at an analysis example of an IPM motor with no rotor overhang. If we look at the flux linkage in the coil and compare the 2D and 3D results, we see that for the coil linkage flux at 10 amps, for the 2D analysis is about 13% lower than in the 3D analysis. This is all due to the flux linking the coil ends. So, if we want an accurate estimate of inductance, we actually need to run a 3D analysis to capture that leakage flux. In our next example, we can see how losses are affected at the ends of a model. In the analysis example below, we're going to look at an SPM motor with overhanging magnets. These overhanging magnets contribute to in-plane eddy currents that are induced by the leakage flux from the magnets on those motor ends. We can see in this finite element model view that the magnet itself is overhanging and the rotor and the stator are at approximately the same height. If we look at the loss distribution of the model with overhang, we can see that the losses are fairly low but increase exponentially with actual rotor speed. We see that if we include the effects of overhang, that the losses due to that overhanging magnet actually contribute to a significant portion of the total losses in the machine. If we are going to accurately capture the losses, we need a 3D model to capture the effects. If we get back up one slide, capture the effects of that overhanging magnet. Another example is to look at the eddy current distribution in a laminated steel sheet. So eddy currents induced by magnetic flux and the in-plane magnetic flux and their effects on the magnetic flux can be found only using 3D analyses. In this example, we'll look at an SPM motor model with a single sheet of laminated steel. If we look at that lamination sheet, we can see that the eddy current distribution is affected by the lamination. The eddy currents that are flowing move to the skin of the lamination sheet, and this affects the magnetic flux density. So, the magnetic flux induces eddy currents in the skin depth of the steel sheet, and this results in a non-uniform flux density in addition to eddy current losses. So, we can see that the eddy currents are flowing, and then if we look at the magnetic flux density as a function of the distance from the steel sheet surface, we see that we have a non-uniform magnetic flux density due to the eddy currents forcing the flux to the outside of the steel sheet. Going along with the eddy current theme, we can also investigate magnet eddy currents in PM machines. Knowing the eddy currents in a magnet is important for finding ways to prevent demagnetization. 3D analysis is essential for accurately evaluating eddy currents inside a magnet. In this next example, we'll look at an IPM motor and find the relationship between the magnetic divisions in the axial direction and the eddy current loss. Eddy current loss can be reduced by dividing the magnets. And so if we look at the eddy current distribution in a single magnet, we can then capture the results of the losses and then look at it, as we increase the number of divisions in the axial direction, how much we can reduce the total losses. So the blue line is the loss per a single magnet division, and the pink line is the total losses. So we can see that going from one or a single division in the axial direction to two divisions in the axial direction result in a fairly significant reduction in losses. But going from 2 to 4 to 6 and beyond doesn't result as significant of a reduction in losses. So now we can track what the losses are, and we can find where we get the most quote-unquote bang for your buck as far as increasing the number of divisions without increasing the total number of components. Another 3D effect is the skew effects. Skew is normally set ignoring axial direction magnetic flux. However, flux increases in the axial direction due to skew. So motors in recent years have extremely small cogging torque, so it's necessary to account for axial direction magnetic flux in order to accurately evaluate cogging torque. In this analysis example, we'll look at a step-skewed motor with a skew angle of 15 degrees, and we'll examine the cogging torque obtained with a 3D and 2D analysis. The difference between the 3D analysis and the 2D analysis is the 3D effects of the axial direction magnetic flux. This has a fairly large influence on the cogging torque. So, the blue line is a 3D cogging torque with a lamination factor of 100%, and the green line represents the cogging torque for the 2D analysis. The pink line is the difference between the 3D and the 2D cogging torque, and as you can see, the pink line is a fairly significant value. In order to accurately capture the cogging torque effects for this skewed motor, we also have to account for the lamination factor of the steel. So, what we can do is compare the cogging torque results for a lamination factor of 98.5% and one with a lamination factor of 100%. So, as the lamination factor decreases, that's going to decrease the permeability in the axial direction and thus reduce the amount of flux traveling in the axial direction. That flux reduces, which means that the cogging torque also reduces. So in order to actually capture the cogging torque, we also have to accurately set the lamination factor, because that's going to have a significant impact on the total flux that's traveling in the axial direction, and thus the total cogging torque. Another 3D motor effect is eccentricity. Eccentricity in a rotor's axis can cause vibration and noise. With a 3D analysis, eccentricity can be set with an axis offset or an axis inclination. In a 2D analysis, we'd only be able to do the offset, but we wouldn't be able to do the rotation. But now that we're using a 3D analysis, we can add the effects of a 0.2 degree rotation as well as a 0.04 millimeter shift. Now, if we look at the results of this analysis, we can see that the electromagnetic force on the rotor is relatively high in the x-axis and the y-axis. So that would result in an eccentricity, which could then lead to noise and vibration in the machine. So performing 3D analyses. Some initial impressions of 3D analyses are based on some of the feedback that we get from our customers. So one of the first questions is, isn't creating a geometry in 3D hard, or is it difficult to make coil end turns? Material settings we'll skip over during this webinar, but we'll get into condition settings, and one of the questions that we see is, isn't it harder to set the analysis conditions on a 3D model? Once everything is set from the geometry and the conditions, then isn't it difficult to create a mesh for a 3D analysis? And won't running a 3D analysis with that larger mesh increase the analysis time? Finally, when we get to the results evaluation, some people ask, what's the point? Why would you go through the trouble of doing a 3D analysis if you're still only going to evaluate the same things? Well, let's get to some answers and then get into a demonstration of these answers. As far as geometry creation goes, no, it's very easy to extrude a 2D model into a 3D model or import a 3D model from a different CAD program. For the coil end turns, you can either bring them in based on your 3D CAD geometry, or you can use a template tool in JMAG to automatically create the coil end turns. For the condition setting, isn't it hard to set the analysis conditions? Well, no, in JMAG it's just like setting the conditions in a 2D model. As far as mesh generation, JMAG has automatic mesh generation tools to help reduce the number of elements in a 3D model. When you actually run the analysis, isn't the analysis time going to be too much? Well, no, there are special ways to reduce the analysis time, such as high-speed solvers, and we'll go into these a little in the second half of this seminar. As far as the evaluation goes, it's kind of the key question. So you go through the trouble of creating the 3D analysis, but you're still only going to evaluate the same thing, so what's the benefit? Well, with a 3D analysis, you're going to get more accurate results than you would if you would just rely on a 2D analysis. So let's pause here and move over to JMAG and look at how we can create a 3D model. So I'm going to go to our 2D model that was created based on JMAG Express, and we can see that this is just a standard 2D model and just went into JMAG Express and exported the model into JMAG Designer. Now, in JMAG Designer, I can right-click on the solid model itself and extend the model to 3D automatically, or I can go to our geometry editor and then move the sketches to new parts and then extrude the parts. So what we'll do here is I'll just extrude this stator by 10 millimeters, and I'll go to the rotor and move that to a new part, and I'll extrude that, but I can also add a skew on that rotor. So let's put a 5-degree skew on the rotor. So now, if I go back to JMAG Designer, I can update that model, and we'll have a full 3D model, including the effects of rotor skew. So again, you can see it's very easy to take a 2D model in JMAG and convert it to a 3D model. We can also, in this next example, bring in a model from our CAD program. So in this case, instead of linking to our geometry editor, we actually have a CAD link to a SolidWorks model. So this model was imported into JMAG, and then once we're in JMAG, if we create a study, but then modify our model in SolidWorks, we can automatically update the model in JMAG. And when we update the model, all the settings that we've created in JMAG stay intact. So this was our initial model. You can see it's a 90-degree symmetry model. And this is our modified model, which is a 90-degree symmetry plus a half-axial symmetry model. All the settings and everything else that we would apply stay intact. So again, it's very easy to create the model in JMAG. Once that model is in JMAG, and this is a model that has no parameter set, it's very easy to create the model settings. So the same as with 2D, we can take our material conditions, and let's put a magnet, a 42 MGOE sintered magnet, or sintered neomagnet. Let's just go with 44. We'll drag that and drop that condition on. And then we can set our magnet direction as parallel to an edge and easily set our magnet direction. So we can go through and set our material properties just by dragging and dropping as we would do in a 2D analysis. And we can do the same for our model analysis conditions. So we can set a rotation condition by dragging and dropping onto the rotor and selecting the rotor and the magnet. We can set our FEM coil conditions by dragging and dropping that condition onto our FEM coils and go through and set our analysis conditions. So, in terms of setup time, a 3D analysis and a 2D analysis are virtually identical. But what about actually running the analysis? Isn't that going to take a long time? So let's go back to our model and see how we can increase analysis speed in 3D analyses. So even if a 3D analysis has numerous benefits and, as we've seen, isn't that much more difficult to set up than a 2D model, it does you no good if the calculation time is too long. So let's look at some ways to reduce the calculation time by making use of machine resources and looking at high-speed calculation techniques. So making use of machine resources would be classified as hardware techniques, while high-speed calculation techniques would be more software-based techniques. So machine resources. Speed increasing techniques using machine resources have developed in JMAG. Currently, there are three main ways to make use of machine resources. These are parallel processing, GPU, and distributed processing. What is parallel processing? Well, parallel processing uses multiple cores to complete a single task. Shared memory multiprocessing, or SMP, and distributed memory multiprocessing are the two different methods that we have to use parallel processing. SMP uses processing distributed across multiple cores. So if you have a single machine with multiple cores, you would use the SMC processing technique. DMP is processing distributed across multiple machines connected in a network. So DMP isn't based on a single machine, but multiple machines. So you take your single model and then break it down into smaller models and then send those models out to different machines to run the calculations in parallel. What is a GPU? Well, a GPU is your graphics processing unit. And in recent years, GPUs have been undergoing a revolution and are now able to contribute to calculations in high-performance computing systems. Parallel processing using GPUs is also possible in JMAG. We also have distributed processing, where large numbers of analysis cases can be completed in a short time by distributed processing functions using a network environment. So multiple analysis cases can be sent out to individual computers on a network, and the results sent back to that main management server and then analyzed. There are also high-speed calculation techniques that are based on software tools. These are the steady-state approximate transient analysis, the time periodic correction method, the A-phi calculation method, the gap flux boundary condition, and the rotating machine mesh from periodic mesh, automatic extruded mesh, and extended slide mesh. So the steady-state approximate transient analysis is a way to reduce the transient time in a machine. In induction machines that use a voltage power supply, they require a lot of time to reach steady state because of the effects of the secondary conductor. A steady state is achieved faster by restarting from an approximate steady state. Calculation results from sinusoidal waveforms using the power supply frequency are generally used for approximate steady state calculations. So effectively what we're going to do is we're going to force this machine to go right into steady state operation by setting the rotational speed and the slip conditions for this induction machine. So without the approximate steady state analysis, we're going to have to go through the entire transient phase in order to get to our steady state operating condition. With this approximate steady state condition, then we're going to force the steady state operation right from the beginning. So effectively, we're going to go right into steady state operation. The drawback is we have to set the steady state conditions. So we have to actually know information about what the steady state operating point is going to be ahead of time before running the analysis. JMAG also has a new A-phi method. ICCG convergence improves when the A-phi method is used in eddy current analyses, but the number of calculations increases because there are more unknowns. JMAG employs a process to achieve the same increase in accuracy by managing the ICCG method's pre-processing, which reduces the number of unknowns. So, in a typical A-phi method, we have a certain number of unknowns. This would typically lead to an increasing in the calculation time just because there are more equations to solve. But JMAG can reduce the unknowns, which also reduces the number of equations to solve. In a 3D IPM motor, the number of iterations is about 1/4 of the A method when we use the A5 method, and the ICCG calculation time is about 1/3 of the actual time that the A method would use. So we can see we get better and faster convergence with the A5 method as compared to the A method. We also have tools such as the gap flux boundary condition. Magnet eddy current loss calculation is based on the eddy current losses that are estimated by applying the magnetic field from a 2D transient analysis onto the magnets of a 3D frequency response analysis. So a 3D transient response analysis would generate about 0.07 watts of loss. Our 3D frequency response analysis would generate about 0.08 watts of loss. So about a 12% difference in the accuracy of the calculation, but since we're running a frequency response analysis only on the rotor with a field calculated from a 2D analysis, we can see that our calculation time is about 1/30th the length of a full 3D transient response analysis. We can also do loss separation analyses based on the 3D frequency response. Accuracy is high, or not quite as high as the transient analysis, but the analysis time is substantially faster. So as an initial approximation of losses, this 3D gap flux boundary would be a good tool to use. Rotating machine mesh, automatic extruded mesh, is a way to reduce the number of elements significantly. So when we're using a 3D model, the mesh is divided finely in the axial direction and the number of elements is increased as a result. So the number of mesh elements in this extruded mesh example is 148,000, which is about half the value of what we would use with a traditional method. But the results based from the traditional method and the extruded mesh method are nearly identical, even though the extruded mesh method is nearly 3.5 times faster. At this point, I'll pause and we'll go to the example of the extruded mesh. So in this 3D IPM motor, I've generated a mesh. We'll go to properties using our semi-automatic mesh condition. And if I go to the show quality, we see that we have about 111,267 elements. I've duplicated this study and went to the mesh properties, and the only thing I changed was from the semi-automatic mesh to the extruded mesh. Now, however, if we look at the quality of the mesh, we see that we have about half the number of elements. The extruded mesh is a useful tool to reduce the number of elements significantly without compromising the analysis accuracy. Another nice feature in rotating machine mesh is the extended slide mesh. So high precision calculation of non-traditional motor geometries is possible using the extended slide mesh. This extended slide mesh can apply a slide mesh condition to motors that we traditionally would not be able to run a slide mesh on. So in the case of the spindle motor, we can see we have overhanging components that are interfering with the slide in the air gap. But our extended slide mesh is now able to generate a slide in the air gap and divide the air gap uniformly and improve precision. You can see that we have better waveform symmetry as compared to our traditional patch mesh approximation, and as well as the analysis running much more quickly. So the summary of this seminar. Benefits of 3D are accurate torque calculation during magnetic saturation, accurate estimation of coil end inductance, the inclusion of losses at the model ends, the ability to model eddy currents in laminated sheet steels, the ability to look at the magnetic eddy currents in permanent magnets based on the number of magnet divisions, to be able to include skew effects, eccentricity, and to more accurately capture efficiency. Using JMAG to control 3D analyses, we can use our geometry editor to extrude 2D models into 3D, apply coil ends, or set the analysis conditions. In our JMAG calculation environment, we can use distributed processing, parallel processing, or GPUs to use hardware to speed up the analysis process, and we can use software techniques such as the steady-state approximate transient analysis, the time periodic correction method, the A5 method, the gap flux boundary condition, and the rotating machine mesh. I'd like to thank you for joining us in today's webinar. If you have any questions or comments, feel free to contact us at any one of the following addresses.